So when we have a sorted array, there are many times where we want to iterate through that sorted array, and we can do that pretty simply just by going left to right. It would be useful if we could do the same thing with a binary search tree. And actually we can. We can go through all the values in sorted order and then do whatever we want with them. But it's not going to be as simple as iterating through an array, but it is going to be as simple as going from left to right. What I mean is if we want to traverse through the entire tree and we want to do it in sorted order, we call that an in-order traversal. We want to go through the values in order. So like I said, we want to go left to right because starting at the root node, we know that the smallest values are going to be in the left subtree. So before we even process this value, we want to process the left subtree, the entire left subtree. And the same applies. This is a recursive definition. It's a recursive function to go through them in sorted order. So we go to the 3, and from here we know that all values smaller than the 3 are going to be in the left subtree. So we do that. Now from here we're going to do the same thing. We know all values smaller than 2 are going to be in the left subtree, but there aren't any values less than 2. So we are at the 2. Now, what do we actually want to do with this value? Well, we could do anything we want. We could print it. We could add it to some output array. For now, let's just say that we're printing it, and I'm going to write them up here. But okay, we're going to go ahead and print the 2. Next, before we pop back up to the parent, there could be some values over here. In this case, there's not, but if there were, we would want to traverse the right subtree of this node right after we process the node itself, because we know all values in the left subtree of the 3 are going to be less than it. So any values here are going to be greater than the 2 and less than the 3. In this case, there aren't any, so we don't have to do anything. But we pop back up to our parent, and from here, we know we just processed the whole left subtree. So now let's process this node, the 3, and then let's do its right subtree. Well, it doesn't have one. So same thing. We go back up to the parent. We process this node because we just did the whole left subtree. So 4, we print it. And now it's time to recursively do the right subtree. In this case, we actually have a right subtree for us to traverse. And of course, we know all values here are greater than all the values we printed so far. You can tell that just by looking at it. So now let's start at the 6, but before we can print the 6, let's recursively traverse its left subtree. We get to 5. Before we print 5, let's recursively traverse its left subtree. We get to null. That's going to be the base case of our recursion. So now it's time to print 5 because we just did its left subtree. Now it's time to do the right subtree of 5. It doesn't have one. That's the base case. Then we can return back up to our parent. 6. We just did the whole left subtree of 6. So let's print 6. And now let's recursively do the right subtree of 6. It does have one. So we get to 7. Let's do its left subtree. It doesn't have one. Then let's do this value, 7. And then let's do its right subtree. It doesn't have one. But notice how for every node we went left, then we did the current node, and then we went right. So it is similar to going through an array in sorted order. We are kind of going left to right. It's just different. We're doing pointers and we're doing recursion. Now, even though this is kind of complicated to understand, especially if you're a beginner, it took me a while to understand this the first time I learned about it. The good thing is that the code is really, really simple. Let's take a look. So in-order traversal is another recursive function. We're given some root node like this one, and the base case is similar. If the current node that we're at is null, then we can simply return. There's nothing for us to traverse. That would be the base case when we go down here, or when we go down here, or the right child of here, or of course here, 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 and here. The recursive case though is where we want to run in-order traversal on the left subtree first. So we recursively go to the entire left subtree, and then from here we do the same thing. We go to its left subtree, and then from here we do the same thing. We go to its left subtree, which ends up being null. So we return. And then from this node too, after we've done its entire left subtree, we print the node itself. We print 2, and then we run in order traversal on its right subtree. That's the base case. It's null. So then we're done with that subtree. we're back up to 3. We just processed its left subtree. So now let's print 3 and then do its right subtree. It doesn't have one over here. So you probably get the idea at this point. We go to 4. We've already done its left subtree. So now print 4 and then do the entire right subtree. So recursively, we would do the exact same thing here. Now, what's the time complexity of doing this? Well, in the worst case, and pretty much every case, we're gonna have to traverse the entire tree. So we visit every single node once, and that makes the time complexity the size of the tree. So it is big O of n, the same as if we were traversing through a sorted array. There's no way to get around this. I mean, we have to go to every single node. It can't possibly be less than big O of n. But you might have noticed something. If we were given some random values, like we were given these values, but we weren't given them in sorted order, we were just given them in some arbitrary order, we could sort them using a binary search tree and then get a sorted array. So instead of printing each value, we could have taken each value and added it to some array. What would the time complexity of that be? Well, first, if we were given these values, we would have to build a binary search tree. So for every value, we would have to insert it into the search tree. And we know an insertion into a binary search tree is big O log n, for a balanced tree at least, which is what we're assuming. And we would have to do that for all n values. So n times log n would be the time complexity of building the entire tree itself. And then to traverse it, to build, the output array in sorted order, we would have to do big O of n from this in order traversal. So the time complexity would be n log n plus n. So we can write the time complexity like this. But remember how I said that any constants are ignored? Like, for example, if we had 2 times n log n, we wouldn't care about the 2. And by the way, in terms of math, this is equivalent to saying n log n plus n log n, right? That's the same as 2 times something. It's just adding it together twice. Now, obviously, n log n is going to be greater than n itself, right? As n increases, as it becomes a really big number, of course, this is going to grow faster than n itself. So therefore, this equation down here is larger than this equation up here. And we know that this is equivalent to this, and we know that this reduces to just n log n because we can get rid of the constant. So what I'm saying here is when we have added terms where both have variables in them, we only care about the larger one. We don't care about n here because this is going to be less than 2 times n log n, and we know that that reduces to just n log n. So when we have something like this, we only care about the larger term. So in this case, we wouldn't even care about the n. This is dominated, the time complexity is dominated by the larger term, which is n log n. So basically, what we found here is that to be given some random values and to sort them using a binary search tree, it takes n log n, which is similar to some of the other sorting algorithms that we talked about, like merge sort and quicksort. So sorting, as you can see, is really not going away. I told you that there were a lot more sorting algorithms that you might have thought, and there are a lot more, including some that we're not even going to cover in this course. There's just a ton of sorting algorithms. Now, if you actually want to go through the values in order, which is usually the most common thing with binary search trees, this is the way to do it. But there are some cases where for a tree, and it could be a binary search tree or it could just be a generic binary tree, there are some cases where we would want to visit the root node and then visit its children and do that recursively. So by the time we get to this node, we want to visit this or print it or add it to some array or do something with it before we do anything with its children. We call that pre-order traversal. So let me ask you, if we wanted to traverse this tree such that we visit 4, we print 4, and then we print its entire left subtree, and then we print its entire right subtree, aka pre-order traversal, how would you augment this in order function that we have over here. The good thing is we don't have to change much. We just have to swap the order of these two lines over here. Instead of going through the entire left subtree before we print the 4, we just print it before we go through its left subtree, and then we go through its right subtree. So to make it more clear, this is exactly what that code would look like, printing it before we run pre-order on the left and then we run pre-order on the right. Otherwise, it's the exact same base case, the exact same parameters. Now there's the other case, which we call post-order traversal, which is the opposite. So if we wanted to, for this node, traverse all the values in the left subtree and then traverse all the values in the right subtree and only then print the root node, we would recursively run post-order traversal on the left and post-order traversal on the right and then print the value. So these three functions are very, very similar. We just swap kind of the ordering the way that we do the traversal. That's kind of the nice thing about doing this recursively. It's hard at first to wrap your head around recursion, which is why I've really tried to emphasize it throughout the entire course. But once you do understand it, things can become really, really simple. So we got in order, pre-order, and post-order. By the way, we could do reverse order as well. Do you know how we could augment this? What I mean is we printed the values in order. We got 2, 3, 4, 5, 6, 7. But what if we wanted to do the opposite? We wanted 7, 6, 5, 4, 3, 2. How could we do that? Well, if we want to get the largest value first, when we arrive at the root node, we should probably go to the right subtree and then print 4 and then go to the left subtree. So then we get to the 6. We should probably go to the right subtree before we do 6. So let's get down here. We should probably go to the right subtree first. There's nothing there. Then we print the 7 and then we print the left subtree. There's nothing there. And then we go back to 6, print 6, and then we do the left subtree, 5, print 5, and then we're at 4, print 4, and then we go here. We would print 3, go to its right subtree, there's nothing there, and then print 2. So that's how we would do it in reverse order. How would you augment the code to do that? Pretty much just swap these two lines. So instead of doing the left subtree first, we want to do the right subtree first, and then print the value, and then print the left subtree. By the way, for all these traversals, pretty much every way that you can traverse the entire tree, the time complexity is going to be big O of n. Now, believe it or not, we just talked about probably the most common algorithm when it comes to coding interviews, and one of the most common algorithms in general. It's called depth first search, aka DFS for short. All three of these recursive functions are examples of DFS. And it's pretty much like the name implies. As we search, we go depth first. So for example, we start at this node and we go in one direction. We could go in the left or we could go to the right. We could process this first and then go to the left subtree, or we could process this after. But either way, it's a traversal. We're going as far deep as we can first. We're not going to, do this node and then do this node and then this, and this. We're going to go as far deep as we can in the left subtree before we go into the right subtree. So we go here, we go to the left, we're going deep as we can down here now, right? In this subtree here, we're going to go as deep as we can. We go to the left node again. Here, we're going to go as deep as we can. This is what we did first. This is the first thing we did. We reached the bottom of the tree. We went depth first. We got to the bottom of the tree. This is the first thing that we did. We went as far deep as we could in one direction before we even visited any other node. And obviously the tree could have been even larger, but you probably get the idea. And we would have done that with all of these functions, whether they go in the left subtree first or the right subtree, whether we process the first node before or after, it doesn't matter. We go deep first and we pop back up again, and then we get here, and then we recursively run DFS on the right subtree. We go as deep, starting from 6, we go as deep as we can. We go to the left child here, 5, and then we keep going. There aren't any children, but we did the same thing. We went as deep as we could, and now we pop back up to 6, and then we go as deep as we can in the right subtree. There's only a single node, but you get the idea, right? We're going depth first. So imagine for every leaf node, we're going as deep as we can for every single leaf node first individually. Now, it's hard to understand DFS without understanding an alternative way. I kind of glossed over it a second ago. The opposite of DFS would be breadth first search, aka BFS, and for that, we would go layer by layer. We would go the first layer, just this node itself. Then we would do, this node and this node. We would do this entire layer, and then we would do this entire layer. This is clearly not depth first search because we're not reaching the bottom immediately. We're kind of going, like this. And breadth first search is actually what we're going to start talking about up next.